Ionic equations. Neutralization is a phrase that we've just seen, and it's a great opportunity to practice our ionic equations skills. Okay, we saw them earlier on in the course, but we haven't practiced them much. This is the perfect chance to put some into action. So, ionic equations, essentially they only show what's really changing in a reaction. They only show what's reacting. For something to react, it has to change in the way that it bonds, in its formula, in its structure. If it's just the same on the left-hand side and the right-hand side, then it essentially plays no part in the reaction. So we follow certain rules. First thing we do when we're trying to write an ionic equation is we write a full balanced equation. Remember, get the formulae correct before you start balancing. If we're reacting sodium carbonate, which is aqueous, it's soluble. It's one of the few carbonates that's soluble. We'll talk about that later. Most carbonates are insoluble. We react it with sulfuric acid. You can try and write down what the products are. Acid plus carbonate. So stop me if you've got the urge to try that. There you go. Sodium sulfate, which is also soluble, and water and carbon dioxide, which is gaseous. Right. Then the second step is we have to break up the soluble ionic substances, the aqueous substances. So what does sodium carbonate consist of? Well, it consists of 2 Na pluses per mole, doesn't it? 2 Na pluses and 1 CO3 2 minus. Both of them are aqueous. What does sulfuric acid do when it breaks up in water? It gives me 2 H pluses, which should be aqueous, and 1 sulfate ion, which is aqueous. Okay. Sodium sulfate, similar kind of idea, 2 sodium ions and 1 sulfate ion. Water, well, water isn't ionic, it's covalent. Carbon dioxide isn't ionic, it's covalent, so we can't break them up. And that's it. That's the first, well, that's the second rule, the first real step, breaking up the soluble ionic substances. Then, there's the equation again. We have to identify and eliminate the spectator ions. So we look at what we've got on both sides of the equation that hasn't changed. The sodium ions, if you look at them on both sides of the equation, they have not changed. So they're called spectator ions. The sulfate ions on both sides of the equation have not changed. Spectator ions. So what we do is we take those ions away, essentially cancel them, and we write what's left. CO3 2 minus aqueous. 2 H pluses are there, and what do? They make water and carbon dioxide. You have to make sure that everything you've got on this side is the same as what you've got on this side. You've got the same number. Also, as well as balancing for species, having the same number of carbons, the same number of hydrogens, the same number of oxygens, etc., they also have to balance for charge. These ionic equations must have the same charge on both sides. On this right-hand side, there's no charge. So on the left-hand side, how can there be no charge? We've got 2 minuses and we've got 2 pluses. 2 pluses and 2 minuses cancel out, no charge. That's called the ionic equation for this particular reaction. Let's try another one. Hydrochloric acid with potassium hydroxide. There you go, you can have a try at that. Potassium hydroxide and hydrochloric acid, they react to give potassium chloride and H2O. You need to copy these down onto your notes. If you need to, you can stop me at any point. Then we're going to step 2, break them up into their ions. So potassium hydroxide breaks up into K pluses, aqueous, and OH minus aqueous. Hydrochloric acid into H plus and Cl minus chloride ions. On the right hand side, same idea. This breaks up, but the water doesn't because it's covalent. Cancel the spectator ions, or which ones are the spectator ions? The same on both sides. Bing bang, bing bong. They're the same, aren't they? What are we left with? Rearranging slightly, we're left with that. And this is quite a special ionic equation. It's called the Ionic equation for neutralization. So whenever a hydrogen ion encounters an OH minus, a hydroxide ion, a water molecule is formed. This is neutralization. Okay, all good stuff. There it is again. That's an ionic equation. Something to keep in mind is that when you are neutralizing something, when neutralization takes place, you're getting rid of ions and you're making molecules. So the number of ions decreases. So the conductivity of a particular solution, how much electricity it conducts, also changes. And we can actually use that fact to see how this reaction proceeds. We could actually use it to show when neutralization has actually happened. That's just a little aside. It might pop up somewhere. Proton transfer. Right, what's a proton? Well, a proton's in the nucleus, isn't it? If I take a hydrogen atom and I take away the electron, which is what I do to make H+, I take that electron away, I'm just left with a proton. Okay? So an acid is considered to be a proton donor. It gives this proton to other things. Okay? So we've got that proton in acids, and acids are proton donors. Let's take an equation that we're familiar with. There you go. The hydrochloric acid here is a proton donor. What does it do with its proton? It donates it to a base. So a base is a proton acceptor. Proton donors, proton acceptors. Here's another example. The acid is the proton donor and the base is the proton acceptor. It's a very important distinction. Here's another example. Look, you've got a hydrogen chloride molecule and it can give its proton to the water molecule and you make this funny ion. It's called H3O+. It's called an oxonium ion and a chloride ion. So this is my proton donor and this is my proton acceptor. Water is acting as a proton acceptor. Okay, the applications of acids and bases. Now this is something you should have a look at. So have a look in the book, find the pages that contain information about these and try and find 2 uses of acids and bases in everyday life. You'll need these for exams. Right, I'll give you a couple. Vinegar obviously is in many things. It's in the kitchen, it's used to preserve food. And in car batteries, we use sulfuric acid. Vinegar is ethanoic acid. Ethanoic acid. And in car batteries, it's sulfuric acid. Bases can be used to clean things, like ammonia or some hydroxides can be used in the kitchen. And they're also used to neutralize acidic soils. So limestone and lime are used when a soil becomes too acidic and plants can't grow in it. We can add limestone. Farmers, they just spread the limestone onto the soil. Okay, that's just a reminder of that. And it brings the pH closer to 7. Some plants have got perfect pHs, so they play around with the pH. Lime can also be used, but sometimes lime, if it's used, can make, if you add too much, it can make the soil too alkaline. If the soil is too alkaline, what farmers do is they add animal waste, manure, to make it more acidic. It's just playing the pH game to get the right pH for a particular plant. Right, there's some pages for you to look at and some questions for you to answer.